So let me see. Let me just we're in section 5.3. And you've already had some experience with 5.3 in diagonalizing matrices. So when you diagonalize a matrix, what you're doing is you're taking that matrix A. I can use a little highlighter here. Taking the matrix A, and you are constructing a matrix P and a matrix D such that this square matrix A equals P times D times P inverse. Naturally, P and D are also square matrices. So, of course, the matrix P consists of the eigenvector. Well, first of all, what do? What's the first thing you have to do when you diagonalize a matrix? What's the first thing that you have to do? What's the first thing you have to find? Good, Matthew. You have to find the eigenvalues. So the eigenvalues form that diagonal, along the diagonal of matrix D, D for diagonal, you have your eigenvalues. What does the matrix P consist of? What does the matrix P consist of? Eigenvectors. Very good, Matthew. And so, you're finding eigenvalues and eigenvectors. And for instance, if you have a 3x3 matrix A, then the matrix P has to consist of 3 linearly independent eigenvectors. Now, if you can't find 3 linearly independent eigenvectors, then you can't diagonalize the matrix. Okay, and you had a few problems in your homework where you couldn't diagonalize the matrix. Okay, all right. Now, maybe what I'll do is show you why this works. Okay, let me just show you why this works. So you're familiar with the process, and again, I'm going to give you instructions for exam 3, but diagonalization is something that I would expect students to work through by hand, showing row operations. Okay. How does the diagonalization theorem work? Okay. So you have a n by n matrix, and again, they're saying the matrix A equals P times D times P inverse, where D is a diagonal matrix and the columns of P are linearly independent eigenvectors. So why can this be done? Why is this true? Why is this diagonalization theorem? Okay, why is it true? Well, let's go ahead and look at their little proof here. Okay, let's look at their proof. So what they do is they say, let's suppose P is an n by n matrix with column vectors v1, v2, v3 up to vn, and D is any diagonal matrix with diagonal entries lambda 1 through lambda n. Okay, that's what we're doing here. Okay, so what they do is they say, well, all right, if we want to multiply the matrix A times the matrix P, that's the same as multiplying the matrix A times the matrix P, whose columns are those vectors v1 up to vn. And then by the definition of matrix multiplication, you learn that the product matrix, you can write the column vectors as you see here, AV1, AV2, up to AVN. Okay? So that's what A times P is. All right? Now, if you multiply the matrix P times the matrix D, you're going to get the matrix whose column vectors are lambda 1 v1, lambda 2 v2, up to lambda n vn. Okay, and let me just sort of show that to you why that's true. I'll come back to the proof here. Let me go to the whiteboard and just show you you know, why that would be the case here. So, okay, so let's say you had one, hold on here, 1, 2, 3, 4. Okay, 1, 2, 3, 4. And 1, 3 is vector v1, and the vector v2 is 2, 4. And we're going to multiply that 2 by 2 matrix by another 2 by 2 diagonal matrix whose diagonal entries are lambda 1 and lambda 2. So okay, and those are scalars. So you know how to do matrix multiplication. Okay, so okay, this is our 2 by 2 matrix here that results. Now I can write that matrix as the matrix whose first column is lambda 1 times 1, 3, and whose second column is lambda 2 times 4, 2. All right, is that, so all I'm doing is I'm taking 2, 4, thank you, good catch, good catch. Thank you, one moment here. Well, you're gonna see, What I'm trying to do, the reason I'm doing this is in the proof of theorem 5, the diagonalization theorem from section 5.3, there's a statement, the statement number 2, I'm trying to make you feel comfortable with that. So this just equals lambda 1, hold on here, one moment. Okay, this equals lambda 1 times v1. Okay, so, and then you got lambda 2 times v2. Are there any questions on this? So what I'm trying to demonstrate here, what I'm trying to demonstrate to you is that if you take a matrix, with and you look at the column vectors of the first matrix, and then you multiply it by a diagonal matrix, Okay, then the product matrix, the columns of the product matrix are lambda 1 times the first vector, the first column, and then the second column is lambda 2 times the second column, you know, from the V2. Are there any questions on this? Okay, so keep that in mind. Keep that in mind. What I want to do now is go back to the textbook. I want to go back to the textbook to that proof. Okay, so let me go back here. Okay, so now this statement that P times D, okay, where P's, the column vectors of P are V1, V2 up to Vn, P times this diagonal matrix D equals that product matrix whose column vectors are lambda 1 V1, lambda 2 V2 up to lambda n Vn. Now that makes sense. Now let me ask you a question. Suppose A is diagonalizable. Okay, and maybe what I'll do is go back to the blackboard to the whiteboard for a moment. Okay, so if A is diagonalizable, so we're assuming in this part of the proof that A is diagonalizable. That means A equals P times D times P inverse. But we're still trying to establish why the matrix P consists of eigenvectors of A and why the matrix D is the diagonal matrix of eigenvalues of A. That's what we're trying to prove here. You've gone through the process where you found P and D, but I want you to know why it's true. So what we can do is we can, on the left side, hold on. No. Hold on. One moment. So assuming A is diagonalizable, watch what I'm going to do here. I'm going to multiply on the right side by P on both sides. And indeed, Biniam, P inverse times P is the identity. So you get that A times P would equal P times D. So that means that if A, I'll just put this in for the recording, kind of a big word here for the, that's okay. So A being diagonalizable, hold on, let's make it nice. It's all about quality, right? All about quality. A being diagonalizable implies that A equals P times D times P inverse, but ultimately then, since P is invertible and all that, this means that AP equals PD. And that's what we have. That's what we're going to look at in Theorem 5. Now let me go back to the book. Are there any questions? Okay, let me go back to the book. Hold on here. Good, good. All right. So now in the proof, we have AP and we have PD. And AP has to equal PD. This means the following. This means the following. Okay. If AP, actually hold the phone. Okay. So if AP equals PD, then what's A times V1 have to equal? That's right, Binyam. Lambda 1 times V1. What's A times V2 have to equal? That's right, Sega. Lambda 2 times V2. And so forth. Well, if A times V1 equals lambda 1 times V1, what's that tell you? I mean, if we focus here, I don't want to do it. So it's all in the recording, all of this. But let's focus here. A V1 would have to equal lambda 1 V1. Well, if A times V1 equals lambda 1 times V1, what can you tell me about lambda 1, that scalar? What must lambda 1 be? So A times some vector V1 equals some scalar lambda 1 times vector V1. What would the scalar lambda 1 have to be for that to be true? No. Here, all right, hold on. Here's what I'm saying. Let me go. Hold on. Here's what I'm saying, okay? So we agree in the proof that A times V1 would have to be equal to lambda 1 times V1. Right? Those columns are matched. What's that the definition of? It's the eigenvalue. Right. Lambda 1 is the eigenvalue. Good, Binyam. What about V1? What's V1, the vector V1? V1, good, Matthew. V1's an eigenvector. So lambda 1 is an eigenvalue, and the vector V1 is the eigenvector corresponding to lambda 1. Now also, we had that A times V2 was equal to lambda 2 times V2. Oh, what's that mean about lambda 2, the scalar lambda 2? Lambda 2 is an eigenvalue, and then V2 is good, everybody. V2 is the eigenvector corresponding to lambda 2. So you see then, if we go back to the proof, it's clear that this based on the matching of the columns, it's clear that the matrix P, that consisted of columns. Remember, the matrix P consisted of columns V1 through Vn. Well, those vectors V1, V2 up to Vn are eigenvectors. And the matrix D, the diagonal matrix consisting of the scalars lambda 1, lambda 2 up to lambda n, those scalars are eigenvalues. And that's why this works, this diagonalization procedure. That's why you construct the matrix P with the eigenvectors of the matrix A, and you construct a diagonal matrix D with the eigenvalues of the matrix A. P is the P, an eigenbasis is, there are if you have several eigenvalues, you're going to have several eigenbases. But P consists of all the vectors together from all that form the bases for your eigenbases. So the matrix P is all the eigenbases put together. Let's put it that way. Okay, all right. And that's why this works. Very good, Binyamar. How many think that's like one of the most beautiful proofs they've ever seen in their life? You know, I think Christy likes it. Ryan likes it. Sega, Robin, yeah. Now you know why. Now you know why it's true. Kevin likes it. Great. Okay, very good. So let us proceed on here. Binyam says it's crazy. I hope it means it's crazy good. But I'll take it. Good. So on that note now, let's go into the book a little bit here, a little bit more. I want to go back and show you, so you might wonder, well, why is diagonalization helpful? Why is it helpful? Well, first of all, in example 1, they talk about a matrix D. Now, matrix D, let's say it's D is diagonal matrix with the entries 5, 3. D squared here, if you take a diagonal matrix times a diagonal matrix, the product is going to be just the diagonal matrix with the diagonal entry squared. Okay, do you see that? Okay, good. Yeah, it's interesting. Okay. We're all good here. Okay, so my screen's good, right? Can people see people can see example 1? Okay, good. Thank you, everybody. So the example 1, D is this diagonal matrix, and if you square the diagonal matrix, you're doing matrix multiplication, the product matrix is just going to be the matrix with diagonal entries that are squared. If you do D cubed, that's just D times D squared. D cubed is just going to consist of the diagonal matrix where the diagonal entries are cubed. And in fact, D to the kth power is just equal to the diagonal matrix with, along the diagonal entries, 5 to the kth power and 3 to the kth power. Okay, so now, why is this helpful? Well, let's look at it. Well, first of all, are there any questions on that? So far, so good. Okay, good. Well, let's go to example 2 now. Why is diagonalization helpful? Well, let's say in example 2, you have a matrix A. And let's say that A equals P times D times P inverse. In other words, A is diagonalizable, where P consists of, P is that matrix, and D is this diagonal matrix. And then you can get the inverse easily for a 2 by 2. Okay. Well, all right, let's say you wanted to find out what A squared is. A squared would just be P times D times P inverse times P times D times P inverse. But matrix multiplication is associative. So we can, the P times P inverse in the middle is just the identity. And so A squared will equal P times D times D times P inverse, which is P times D squared times P inverse. Well, that's just going to equal then this here. Okay. So A squared is P times D squared times P inverse. On the other hand, A cubed, okay, turns out A cubed is, by the fact that you got P inverse times P in the center here, which is the identity, that's going to equal P times D cubed times P inverse. So in general, A to the kth power is equal to this product of these three matrices. And along the diagonal in the middle, you have 5 to the kth power, 3 to the kth power, and it allows you then to get formulas for the entries of A to the kth power. You might have, Matthew. Yeah, there was something about this. A lot of times I give problems where it kind of forecasts for you what's coming up. You did see A equals P times D times P inverse. You have seen that before in the past. But here's one of the great applications. Other students remember it too. Solomon and Binyam remember it. Try taking the matrix A on your calculator. Try taking the matrix A, like type this 2 by 2 matrix A on your calculator. And let me just see here. I'm wondering what's going to happen if I take the matrix A on my calculator, okay, and raise it to the 100th power. I'm just trying it right here, typing in the matrix A, and you can do it too. So the matrix A is 7, 2, negative 4, 1. Okay. Okay. Sorry, I had to take care of a little mosquito there. He got a little too close. Got into my airspace, you know. And I never like to kill anything, but you know, these little bugs can cause problems. Right. So if I take A and raise it to the 100th power, okay, I get some very big numbers. Okay. I'm just wondering, let me raise it to the 1000th power. I get, okay, try raising it to the 1000th power. Matrix A times the 1000th power. And you get something, you know, calculator can't handle that. But the point is, what I'm trying to show here really is that, I mean, think about if you were, here's what I'm trying to say. We have, by the fact that A is diagonalizable allows us to take any matrix, raise it to any power we want, and we can get the entries of A to the kth power using, but we have formulas for the entries of A to the kth power. Okay, we have formulas. And would that save on computation time for a computer? If we could have formulas for the entries of A to the kth power, is it better to take, like if we were to take A and raise it to the 100th power, is it better to do 100 matrix multiplications, or is it better to use the formulas, to have formulas that you see here? Ryan and Christy say the formulas. Absolutely. Well, this is one of the beauties of diagonalization. It's one of the nice applications of diagonalization for a matrix. And there are going to be some other nice things as well that you'll see. But are there any questions on that? Okay, very good, very good. Maybe one more thing I'll point out here in this section, if we're good with that. Then we're going to move on to section 5.5. You do have theorem 7 here. That is a theorem regarding diagonalization. And the part B is one that's, I think, very important. If a matrix is diagonalizable, if and only if, okay, a matrix is diagonalizable, if and only if the sum of the dimensions of the eigenspaces equals n. How many noticed this in doing their homework? That has to be true. Yes. And and you had problems. Well, yeah, that's absolutely true. And it only is going to happen. I'm looking at then focusing on 2. The dimension of the eigenspace for each eigenvalue equals the multiplicity of the eigenvalue. So the matrices that were not diagonalizable did not have this property. Okay, and so great. Are there any questions at all? Okay, well, very good. Let me